and you should be able to write down your name, and I'll have your record for attendance. I notice, okay, so some people saying not in as well, no data. Let me just make sure that I put your name down. No, I did. Okay, I did. All right. Okay, so welcome everybody. I hope you had a good week. We're getting ready for the second session of this semester's program. And there will be, I'll mention it now, but we'll have a bigger announcement toward the end of today. So I think the certification program is happening. Hopefully, Deborah will join the chat toward the end. Oh, she's here already. Actually, Deborah, maybe do you want to start off by telling everybody about the certification program and how to RSVP?
Yes, good evening to everybody. The certification program will be in two phases. One will be in Montserrat and the other one will be in Gamta. So we're having next week, the 25th and the 26th. So we invited some educational stakeholders like for NEMA, the superintendent for NEMA, uh, we sent an invite to her already to be there, and even Maserati, we invited other people to as well. So it will actually be happening next week on the 25th and the 26th. So Maserati, I will send out a letter to everyone before this weekend that yeah, for the set time and the venue for the program. Thank you so much, Andrew.
All right, you're welcome. So thank you for organizing this. I know people have been very excited to get the certificates, so I'm glad that it will happen next week. So one thing that's important is if you are going to come to the certification program, we want a record that an RSVP that you're going to come. So I think Deborah will tell you how to respond, but if you can just let her know directly that you're planning on coming in person, whether it's in Montserrato or whether it's in Nimba, we would like to have full responses so that we know exactly how many people will be there. That will help us plan for the program. And it's actually good that it's Thursday and Friday because there is no class next Thursday. I'll mention that. But if you look at the schedule, there's no class next Thursday, so there's not going to be a conflict with the certification program. Okay, so we'll mention this again at the end of class today, just because some people are maybe not here yet, and if they join in the middle of class, and they're going to be certificated, then they should get a notification tomorrow. They should get a notification today, but we'll also send something in writing. But the most important thing is we need you to RSVP so that we know that you're coming. And this is if you've earned a certificate from either last year or the year before, right? Because we're doing both of these certifications at the same time. Okay. So either from 2025, spring of 2025, or spring of 2024. Okay. Thank you. All right, great. So let's recall what we did last time. We were talking about these rules of exponents and logarithms. We had this page over here that had a whole bunch of rules about exponents and how they turn addition into multiplication. And then over here we had a whole bunch of rules about logarithms and how they turn multiplication into addition. And there was this seventh very important law that log of b to base a was equal to this formula, log of b to base c over log of a to base c. It turns out that if you know this law, you can solve almost all logarithm problems. Anything that involves changing the form of an expression can often be done by applying this law correctly. Okay, so we remember we talked last time about what's the difference between kind of a simple problem and one that really shows some understanding, right? And so what were these kind of more difficult elements possibly of a problem? So one was, so what other elements can we ask for in a student or teacher's understanding of exponential and logarithm rules? So one is, can the rules be applied correctly when the numbers are more difficult to calculate with? A second one was, can a student combine the rules with solving algebraic equations? A third one is, can the student use context to figure out which rules to apply when it's not so obvious? A fourth one is, does the student know why the rules work? Okay, and a good reference for this is this Art of Problem Solving Volume 2, which I sent out on the chat last time. I sent this out in soft copy as a PDF, and in chapter 1 there is, this chapter 1 is all about logarithms. And it's a very short chapter. It's only 7 pages long, and it has versions of all of these types of problems. So it's a good place to look if you want a resource to read some more about this. And in particular, with last week's homework exercise was to come up with your own problem involving rules of exponents and or logarithms and solve it. And the question should require one of these four next level skills discussed earlier. So either more difficult numbers or some sort of algebraic equation or knowing which rule to apply when it's not completely clear or understanding why the rules work. So maybe a few people sent me problems, which is great. And either for some of the people who did or some of the people who didn't, maybe we can spend a little bit of time doing one or two problems that you've come up with on your own. So, is there anyone who wants to volunteer a problem uh, for this exercise?
Yes.
Yes, James. Mhm.
Yeah, let's
Yeah,
see my assignment.
right. So I think I saw
I
this.
have compute. Yes, yes, yes.
Yeah. Okay, so I'm going to look at your assignment. Let's see. I need to make sure I'm getting the correct. Here we are. Okay, so I see one problem from the assignment. So should I do that one? Okay, so James's problem from the assignment was compute log to base square root of 2 of square root of 8. Okay, I think I'm getting this right. Um, okay. And so, James, do you want to just work this one through? Or does anybody else want to work this one through? Would anybody like to present a solution here or just get it started? You don't need to do the entire way. Okay. Okay. I was getting you very clearly before. It was fine that the background noise was fine. I didn't hear it. But if it got louder, I can go to a quiet place. And for those of you who are here, oh, James, great.
Yes, we have to rewrite the expression using exponents.
Okay. Right. So we're going to rewrite using exponents. Great. Okay. So how do we rewrite that? So what you did in your homework was you rewrote square root of 2 as 2 to the 1/2 and square root of 8 as 8 to the 1/2. Right.
Yes.
Okay, good. So where do we go from here?
We simplify by using the product rules.
Hmm. And what does that tell us?
Yeah, we use the product rule.
Yeah. So what's the next so what do we write that that's equal to?
Log 2,
Mm-hmm.
log 8 to the half
Mm-hmm.
base 2
Mm-hmm.
over log 2 to the half base 2.
Perfect. Okay, good. So this is exactly this, rule 7 that I had on the earlier page, right? This is exactly this rule, right? So we had log of b to base a. In this case, we're taking c equals 2. So b here was 8 to the 1/2 and a was 2 to the 1/2. So here we have 8 to the 1/2 to base 2 and 2 to the 1/2 also to base 2. Okay, so we're using that 7th rule here, which is often very useful. Okay. And so now how do we simplify this?
Yes.
Yes, keep going.
1/2
Hmm.
log 8 base 2
Right.
over 1/2 log 2 base 2.
Great. And so these cancel out. And so what does this end up being equal to?
Yes, since log 2
Mhm.
base 2 is equal to 1.
Hmm.
Hello?
Yep. The one on the bottom and on the top.
Then half log, yes.
Yes. So on the top you get log 8 to base 2. So we
On the
need to
top,
know
we have,
what power do you have to raise 2 to get 8?
Yeah, hello, sir.
Hello, yeah, Prince.
We already have the base law to be the same, which is law 2. We are talking
Hmm.
about the division law, here, which is 2, law 2, and law 2. So what would you use a 2 to divide in each of the base, which is 2 divided 1 time into 8 4 times. 4 over 1, which is just equal to 4.
Right. So 8 divided by 2 is equal to 4, right? But this is asking log 2 to base 8. So this is saying, or log of 8 to base 2. So it's saying what exponent do you need to raise 2 to in order to get 8?
Yeah,
So
so
2 to
that
what
is
power
2 raised
equals 8 here?
yeah, 2 raised to the
3,
third
3.
power.
3, exactly. Right? So this
The
is
third
3
power.
over 1, and so we get 3. All right, excellent.
All right.
Okay. So very good. So thank you to James for suggesting the problem. And yeah, so this is exactly right. You have these numbers that are a little bit more difficult. In this example, you could directly say, oh, if I take square root of 2 and I raise it to the third power, that's the same thing as square root of 2 to the third power, which is square root of 8. So it's a little bit easier to do directly if you want. But if you want to do it carefully and make sure that you get everything right, then this is exactly right. You rewrite everything as exponents, use this rule of logs with a convenient base. You're allowed to pick this base to be anything you want when you do the rule. So the most convenient thing to pick is 2. So once you do it with 2, then you use the exponent rules, and now you've transformed it into a problem that uses only standard numbers. That's relatively easy to do. Okay. So, all right. So perfect. All right. Any questions on this?
Yes, sir. Hello,
Yes,
Dai.
Prince. Yep.
I have a concern here to what we have the law of root 2 and base 8. But it did on multiplication. Why now it turns to division? Is that a multiplication parent?
It's not a multiplication problem, right? Because this is a logarithm problem. So this is saying what power do you have to raise 2 to the 1/2 to in order to get 8 to the 1/2, right? So it's asking that's what the log means with these bases. So when we have log of 8 to the 1/2 to base 2, it's saying what power do you have to raise 2 to in order to get 8 to the 1/2? And then what we do is we use this rule of logs. Maybe I'll put it here. This 1/2, we're using the exponent rule, which says that when you have a log, you can always move the exponent down and turn it into a multiplication problem. So that's how we turn this into multiplication, but it is a 1/2 on the outside and a log of 8 to base 2. It's a multiplication problem that still involves a log. So in the end, you still have to evaluate this log somehow to make that work.
So that means just for any instance, if we are going to have law 2 base 8, then
Mhm.
we are not going to even introduce a multiplication rules,
Okay,
right?
so if you were going to have this separate thing, so log 2 to base 8 like that.
Yeah.
Okay.
If we are going to get law 2 base 8
Yeah,
without the rational, I call it the square root.
right.
Plus,
But the point here is, right, it's not going to be the square root, it's going to be a cube root, right? So we know that 8 to the 1/3 is equal to 2, because it's a cube root, and that's the same thing as saying that log of 2 to base 8 is equal to 1/3. Sorry for the small writing. Make it bigger here.
yeah. Thank you.
Does that make sense? Okay. You're welcome. Other questions? Okay, so maybe let's do one more example, another one of your examples. So did anybody else come up with a problem for the assignment? Okay, well, you know what? Actually, if nobody has another problem right now, what we can do is there's going to be another part of today where we'll talk about making a problem. So let me carry on. So remember that I want to spend a little bit of time unpacking this example that we did last week, okay? So we had this example last week where x was equal to log 3 base 2, y was equal to log 5 base 2, and we had to evaluate the following expressions in terms of x and y. Okay, and so we did all of these. And then I asked kind of offhand, last time, I was like, evaluate log of 300 to base 30, again, in terms of x and y. What is going Okay, and so I just kind of asked this casually. Can you evaluate log of 300 to base 30 in terms of x and y? And one person did submit a solution. I think Victor Johnson submitted a solution that was correct. So Victor, I don't know if your connection is good enough, but if it is, do you want to present your solution here for how you did this problem? And if your connection's not good enough, I'll do it. Okay, so I'll just do this. So the idea for this is to use convert all bases to 2. Okay, and if you convert all the bases to 2, what does that mean? You get that log of 300 to base 30 is equal to log of 300 to base 2 divided by log of 30 to base 2, right? This is exactly this same rule that you can always change to a new base. You get 300 on the top, 30 on the bottom. And now what you see is that if you factor 300, what is 300? So 300, you can write it as 5 times 3. Well, actually, you can write it as 5 squared times 3 times 2 squared. So this is an exercise, but you can verify that 300 is equal to 25 times 3 times 4. That's going to give you 300. And similarly, 30 on the bottom is the same thing, but it's going to be log 2 of 5 times 3 times 2. Okay. And now you can use the rules of logs. So that's log 2 of 5 squared plus log 2 of 3 plus log 2 of 2 squared. And on the bottom, we have log 2 of 5 plus log 2 of 3 plus log 2 of 2. And now, since I don't have that much space, I'm just going to say these squareds go over, because of these rules of logs, you can take this exponent square and put it outside. Yes, Linford, question?
Yes, I did my solution, just that the
Uh-huh.
network was very bad. Did my solution and I wanted to post it so that we can all look at it, please.
Oh, okay. All right. So I can give you permission to share. Okay. Do you want to
All right.
for this problem?
Yes, for the practice problem, sir.
Okay. Great.
I should go ahead and read it,
You
right?
can share. You can share.
Oh, okay. So it's log,
Oh, okay. Okay. You're not going to share
log.
visually. You're just going to share. Okay. So let me put a new page.
All
Okay.
right,
So
thank
what do
you.
you have?
I have log,
Mm-hmm.
okay, base radical 3.
Oh, okay. Oh, so your other teacher problem. Okay. You know what? Let me just finish this first, and then you'll share yours. Okay.
All right,
So let me just
thank you.
finish this one first because I'm in the middle of the problem, and then you can share yours. Okay. So in the middle of this one, so this is going to become, this is 2 log 2 of 5. So this here is just 2y because that's what log of 5 to base 2 is. This is log 2 of 3, so that's x. And 2 times log 2 of 2, that's just 2 times 1 because log 2 of 2 is 1. And down here, you have log 2 of 5, which is y, log 2 of 3, which is x, and log 2 of 2, which is 1. And so the final answer, which unfortunately we have to write up here, so the final answer is going to be 2y plus x plus 2 divided by y plus x plus 1. Okay.
Is that the power rule you use?
Yeah, we're using the power rule. This is what I kind of drew here. The power rule is moving these twos down so that they become multiplication instead of exponents, right? So the 2 is moving here and the 2 is moving here. That's why we get 2y here, regular x, and then we get 2 times log 2 of base 2, which is 2 times 1. So that's what we get, 2y plus x plus 2. And then down here, we don't need to use the power rule. Here, it's just y plus x plus 1. Okay.
Okay.
Okay, great. And maybe I'll just mention here also that why did I come up with this problem? Right? Why did I come up with this problem? Well, once you do this problem, you realize that it doesn't really matter what numbers you put here and what numbers you put here, as long as they can factor into products of 2s and 3s and 5s. As long as you can make your thing a product of some 2s, some 3s, and some 5s, then you can solve this with the exact same methods, right? So 15 here is 3 times 5. 7.5 is 3 times 5 divided by 2. Here you have a 3 and a 5 and a 5 and a 6. And what all these numbers have in common is that you can make them all by multiplying or dividing some powers of 2s and 3s and 5s. Okay? And if you do that, then all you have to do just like this problem, is convert everything to base 2, and then you can factor the numbers out, use the addition rule, and use the power rule, and you can always get your own solution. So if I just wanted to make up a problem on the spot for this with the same given values, so you still have that x is log 3 of base 2 and y is log 5 of base 3, I could say something like, okay, evaluate, log of 1,000 to base 72. And I know in my mind that 1,000 and 72 are both made up of 3s and 2s and 5s, right? 1,000 is going to be 2 times 2 times 2 times 5 times 5 times 5. And 72 is 2 times 2 times 2 times 3 times 3. Okay, so I just picked those numbers, but you can do whatever numbers you want. And as long as you can express everything in terms of 2s and 3s and 5s, then you're fine. Okay? So that's the idea. Okay, so you can easily make up your own problem in this vein just by making sure that everything involves 2s and 3s and 5s. Okay, I'm not going to do it, but I'll leave that as a challenge to you. Okay?
Yes, sir. Yes,
Yes.
sir.
Prince?
Yeah, I have a concern with where you say in terms of x and y. Yes, of course. But then where you have the expression 2y plus x become first and 2, why in case if we use x first to say s or 2x plus y, will it still be the same parent to be used?
Well, yeah, no, if you wanted 2x plus y, remember, so x is log of 3 to base 2 and y is log of 5 to base 2. So here we had 5 squared times 3. This is what became the 2y, and this is what became the x. If you wanted 2x plus y, that would be if you had 3 squared times 5 instead of 5 squared times 3. So if you had 3 squared times 5, that would be 45, and then times 2 squared would be 180. So if this number was 180 instead of 300, then you'd get the same answer, but instead of 2y plus x, you would have 2x plus y, because it would be 2 factors of 3 and 1 factor of 5. But here we
So
had 2
yeah,
factors
okay.
of 5 and 1 factor of 3, so we get the 2y plus x.
Okay, so it means it varies in number, right?
Exactly. Yeah. Your answer will be different depending on the numbers, right? Of course, if I replace a 300 with a 180, the answer is not going to be the same. But what I'm saying is that if you use any numbers that you can make from 2s and 3s and 5s, it is always a reasonable problem, right? So you can ask the problem no matter what your numbers are, as long as you can make them out of 2s and 3s and 5s. The answer will be different each time, but every single one of those problems can be solved by using this method. Okay, so you
Thank
can
you so
make a
much.
problem, and that's why this 330, I wasn't careful about it. I just made up numbers off the top of my head, but I knew that I was using numbers that you can make from multiplying 2s and 3s and 5s. And as long as you do that, the problem will work. It will be a reasonable problem that somebody can do by hand.
All right, thank you
Yeah,
so much, sir.
All right,
that was that.
good. Yes, sorry. Rash?
Yeah, yeah,
Yeah.
yeah. My phone the network is being a little bit hard time, so that's a problem. So it's going to the same problem because I try to explain what you say you look at it. I forget to say because my phone was giving a little problem, man.
Mhm. Yeah, so I
Yeah,
think we were going to have yeah, so you can make a new problem with this by just changing the numbers, and you know what to do. And you don't want to just do any numbers. You don't want to ask log of, 26 to base 7. That doesn't work because you can't make those from 2s and 3s and 5s. But
but they're going to say our x I say is x plus 2y plus 2 divided by x plus y plus 1. I say that again. What you
right,
say you look
that
at
would
it?
be if you had log of 180 to base 30.
Yeah, yeah, yeah.
Yeah. Okay. Okay, so
All right.
Linford, yeah. Let's do Linford's problem. So Linford, do you want to present your problem now?
All right. Thank you,
Yeah,
Darabos.
you're welcome.
Yeah. So the problem is log root 3.
Mm-hmm.
Okay. Log root 3. All right. Onto root 81. 81.
Well, root 81 is 9, right? So why don't we call it 9?
Okay. 9. Thank
Right,
you.
yeah.
Yeah, 9. Yeah.
Okay.
All right. So that was what I did.
Okay. And so how do we
Okay.
do this?
Okay.
So I should go back explaining, right?
Sure. Yeah.
All right. So I went down and then I got log root 3,
Mm-hmm.
log 3 now rather, log 3. Let's take the root, please. Let's
Mm-hmm.
break it down to simplify it.
Yeah.
Log 3 raised to half because we are eliminating now the root.
Mm-hmm.
Yeah, so the nine now
Yeah.
we okay, then we'll come down
Mm-hmm.
log root 3 and half,
Mm-hmm.
okay, onto 3 raised to the power 2.
Mm-hmm.
All right. So here now I use the division method
Mm-hmm.
where I say
Yeah.
log 3, yeah, log base 3 half.
Mm-hmm.
All right. Then I no I express base 3 log base 3,
Okay. A log base 3. Okay.
sorry, yeah, log base 3 onto log 3 square. I'm saying onto 3 square. Okay, okay,
Okay.
just as now
Oh,
it is.
three squared.
All
Sorry.
right.
No, no. Okay. No, no. I'll do it 3 squared. That makes sense. 3 squared. Good.
Okay, 3 square, yeah. Okay, then divide by good.
Mm-hmm.
Log good. All right, 3 raised to the power half.
Great. Perfect.
All
Yep.
right. Then I went back saying half,
Mm-hmm.
half log 3.
Mm-hmm.
All right. Half log 3. Okay. Okay, half log 3 and 3. Good. Divide
Yeah.
by,
I think we need that in the bottom, right?
yeah, yeah,
Mm-hmm.
yeah. Divide by, I hope I'm not getting a bit confused. The division sign,
I think,
okay, yeah, yeah, we need that at the
yeah,
bottom. Good. Okay.
Right, yeah.
Log 3,
yeah.
Mm-hmm.
log 3. Yeah, log 3
Mm-hmm.
and 3. All right.
And
Okay. Raised
what
to
do
the
we
power
have to
2. Yeah.
multiply by, right?
Yes, multiply by, no, log half, the log of there should be half log 3.
Half log 3 of 3,
I'm
right? So
sorry.
so that's this part, right?
Yeah, yeah, the same part,
Right.
yeah.
But what do we get in the
Yeah.
numerator?
Then,
I
yeah,
think
for the
that
for
is
the
two and
numerator,
three
the
power.
3
Mhm.
will raise to the power 2.
Right,
For the
exactly.
numerator, 3 will raise to the power 2.
Right. So we're going to get a 2 over here, right? Right?
Wow.
Because this is the exponent rule. You have 3 raised to the 2, and if you want to,
Okay.
so you have log 3 of 3 raised to the 2. So if you want to
Yeah.
do that, you have to move the 2 down here. So it's 2
Oh,
times log
there where now I
3
got
of 3,
confused.
right?
Yeah, so that there where I got confused now. And then,
Aha. So
yeah.
is it clearer now? So now you're
Hello?
almost done, right? Because log of 3 to base 3 is simple. This is just equal to log 3 to base 3, right? Just equals 1, right? And log of 3 to base 3 here also equals 1. So when you come down to it, this is just 2 divided by 1/2. So you're almost there, right? I mean, this is simplified enough, but the point is these
Okay.
exponents need to come down. So the 2 goes over here and the 1/2 goes over here. That's why we have 2
Uh,
times log 3 base 3 and 1/2 times log 3 base 3.
so the solution will be 2 over 1 over 2, right?
Mm-hmm. Yeah.
Oh, okay,
Or in
okay.
other
Then we
words,
use the fraction. We use the
right,
fraction method. You get to 4. Good.
exactly,
Thank you
right?
so kindly.
Perfect. Yeah, so that's great. And I want to say also, this is a nice systematic algebraic way to do it, but it's also okay if you're given this problem or if your student is given this problem and they need to do it fast and they don't remember all of the rules, then it's okay to just use trial and error, right? What's an alternative solution here, right? Alternative is to just start writing things down. In this case, it'll work. You could say, okay, radical 3 to the 1 equals root 3. Root 3 squared is equal to 3. Root 3 cubed is equal to 3 times square root of 3. root 3 to the fourth is equal to, well, I multiply by another square root of 3. That's going to be 3 times 3, which is equal to 9. Ah, so I see now
Yeah.
root 3 to the fourth is equal to 9, and that means that the log of 9 to base root 3 is going to be 4. That's the definition. So log of 9 to base square root of 3 equals 4. Like, this is completely okay if you can do it. If you don't remember your rules and you want to just try to figure out which power is the right one, you can just try. And a lot of times you'll be able to get the right answer by just doing this. It's not as, comprehensive. It doesn't always work. But if you find yourself forgetting something, or if your student finds them forgetting something and they need to just figure out a way to do this, then this method might work, right?
All right.
So
Thank you, Dad.
you're welcome. Christian, question?
Boss. So,
Yes.
is this division method work in all cases in logarithm?
Yeah, I mean, as long as you choose the right base, right? So if you're just trying to compute something, then as long as you always choose the correct base, this will always work. So, but the point is here,
Or,
you needed to remember to choose 3 as your base to make it work.
okay, thank you.
Yeah, you're welcome. Okay. Okay. Let's move on so that we can, well, maybe any more questions about this? And if not, I want to just move on to today's topic. Okay, good. So, all right. So, one thing that I mentioned very briefly last week, but I want to talk about a little bit more, is that when you're teaching a topic, it's beneficial to be aware of its applications, right? So, if you're just teaching math, I mean, a lot of people will also teach physics or chemistry, but a lot of times your students are going to want to know, or even the teachers are going to want to know, why are we studying this? Okay, you're studying because you want to do well on the WASP, but why do people study this? Usually most math, especially most math in the high school curriculum, was developed because it had applications, okay? Or people have found lots of applications for it. And it may be that you don't have a lot of class time to discuss applications, but you should still know them, even if you don't have a lot of class time, because a student might ask you a question at some point. Oh, I see. All right, I'll have to look over here, but this looks okay. Yeah, so by the way, Victor, this looks good, and you can simplify your 2x plus 2 over x plus 1. You can simplify that to 2, uh, which is, you don't even need to use x and y there. It'll simplify to 2. Um, so, and so it turns out not every topic in the high school curriculum is so easy to immediately have applications, right? I mean, if somebody said, okay, what's the application of using, I don't know, side angle side to show that triangles are congruent? Like, I mean, you can come up with something, but it's not that easy. But one of the reasons I like this topic of logarithms and exponentials is that there are loads of applications that are very interesting and that are good to talk about. Okay, so I want to show you a few of these today, right? So if when you teach this unit, you have, some, I mean, you may know some of them, but I mean, some of these are things that I didn't really completely know before I started preparing for this. Okay, so I think these are all applications that hopefully, if your student has some interest in math, they may also have some interest in some of these applications. Okay, so first of all, what are some applications of logarithms? Well, the old application of logarithms is that before calculators, logarithm tables used to be how you could do multiplication and division and do hard computations. That's kind of a little bit obsolete, and I don't think it's necessarily the best application to give to your students is like how to multiply using log tables. I think it's somehow not so interesting and it's not so relevant for the 21st century where everybody's phone has a calculator on it. So, so whether it's questions, okay, let me mute. Remember, if you don't have a question, please keep yourself on mute. Okay, so one of the major applications of logarithms is just the idea of using a logarithmic scale. So sometimes you have data or you have a measurement that can really take values over an extremely broad range. And when you have something like that, it can often be more useful and it makes more sense to people to present these measurements on what's called a logarithmic scale. Okay, you'll see what I mean when we do these examples. So there's a lot of, very widespread examples of this in the sciences. So the best known is probably pH. So we talk about pH when we talk about whether a substance is an acid or a base in chemistry. And what is pH actually? Well, it's measuring the concentration of a positive hydrogen atom, a positive hydrogen ion in solution. And it turns out that solutions vary a huge amount by how much hydrogen is in them. And it makes much more, rather than saying that this thing has 50,000 times more hydrogen than that thing, it turns out to be much more intuitive to just write this as on what's called the pH scale, where it's much easier to remember, okay, water has a pH of 7 and vinegar has a pH of 3 and so on. Like so this idea of using pH is using logs makes pHs much more comprehensible. So also in acoustics, when people measure volume, this is measured in what's called decibels. This is also it's a measurement technically of sound pressure. And it's also sound pressure can take a wide variety of values. The difference between like standing next to an airplane taking off and hearing somebody speak quietly is not, you can say that one is a certain number of times louder than the other. And it turns out that, one is actually going to be is going to be billions of times louder than the other. And so once you have measurements, if you want to say, well, this thing has a volume of 1 and this one has a volume of 20 billion, that gets kind of hard to understand. Your scale is just too wide. So instead, we use logarithms to get what's called the decibel scale, which I'll talk about, okay, which makes things a little bit more concrete. Another scale that's a logarithmic scale that you may have heard of is called the Richter scale. So this measures earthquakes. This measures how strong an earthquake is. And it's also given in terms of logarithms. So you might say this earthquake was a 5 on the Richter scale, or this earthquake was a 6 on the Richter scale. These numbers, 5 and 6, actually stand for wildly different strengths of earthquakes. And the logarithm helps you convert that into just kind of standard small numbers that are easier to understand. And then the last thing is musical notes. So if you study music, then you learn some names for notes. So the notes could be called A or B or C, or maybe they're called do or re or mi, depending on how you like to study them. But what do these pitches actually correspond to? They measure the frequency of the vibration of the musical notes. And this is also done on an exponential logarithmic scale. Okay, so I'm going to explain all four of these applications and show you kind of how logarithms help you do all of this. Okay, so so by the way, I should also mention a summary of applications of exponentials. We're not going to talk about this as much, but exponentials are used to model exponential growth and decay. So most of you took part in the program last year. So we spent a lot of time last year talking about this exponential growth and decay, and we used these functions to model population growth and radioactive decay and Newton's law of heating and cooling. So if you look back to last April, we did a lot of these modeling. And we derive this by using differential equations, saying a differential equation shows that the exponential is the right thing to model these phenomena. But the fact is, you don't need to know any calculus to do this. In the end, when you're trying to solve problems in radioactive decay, you have your exponential form, and once you have that, you don't actually need to do any calculus. Solving those problems is all algebra. Okay, so if you go back and look at the examples that we did last year, all of them really do not require knowing calculus. Okay, so calculus can help you prove why these are a good choice, but they're not. You don't need to know calculus to use them. So we did cover these in a lot of detail last year, so I'm not going to do this again. I want to spend more time talking about the logarithms, so that's what we're going to do today, as far as applications go. Okay, so let's talk about pH. So what's pH? So in chemistry, the pH of a solution is defined to be negative log to base 10 of A, where A is the concentration of H plus, so it's hydrogen positive ions in the solution. And what is it measured in? It's measured in moles per liter. Okay, so if you know your chemistry, a mole is basically 1 mole of hydrogen weighs 1 gram. But if you forgot that, don't worry about it. It's just, it's talking about how much hydrogen there is. And you take this concentration and you take its logarithm. Okay? And so in general, we say that a solution with a lower pH is called an acid, and the lower the pH is, the more acidic it is. And with a higher pH, it's called a base. So the higher the pH, the more basic the solution is. So pure water has pH equal to 7. Okay, and so what that means, so pH equals 7, what are we really solving there? That's saying negative log 10 of A equals 7, which tells you that log of A to base 10 equals minus 7. And so what's that telling you? That's saying that you have to raise 10 to the minus 7 to get A. So this tells you that A is equal to 10 to the minus 7. So water has pH 7. That means that in standard pure water, there's 10 to the minus 7 moles per liter of hydronium, of plus hydrogen positive ion. But ammonia has pH 11. It's a stronger base. And that means it has 10 to the 11th moles per liter of hydrogen ion. And what is the difference between 10 to the minus 7 and 10 to the minus 11? They both seem very small. It's not a lot of moles. But if you look at these quantities relative to each other, 10 to the minus 11 is 10,000 times less than 10 to the minus 7, right? If I do this, 10 to the minus 11 divided by 10 to the minus 7, well, if I multiply both sides by 10 to the 7, that's the same thing as 10 to the minus 4, which is 1 over 10,000, right? So the amount of hydrogen or of hydrogen ion in ammonia is 10,000 times less than the amount of hydrogen ion in water. Okay? But it's very hard to keep track of measures like, oh, this is 10,000 times less than that, or a million times more than that. So we use this pH scale to turn these kind of widely varying measurements into something that makes sense, right? Into something that's just a little bit easier to understand. I can remember the pH scale. Oh, water has pH 7, ammonia has pH 11. It turns this factor of 10,000 into something very reasonable, a difference of 4. Okay? And so this is a good scale because common solutions differ hugely in terms of how acidic they are. And if you tried to present this data linearly, it would not be easy to distinguish substances on the basic end of the scale. Like, what's the difference between 10 to the minus 11 and 10 to the minus 12, right? These are really, really, really small numbers. It's not that easy to tell the difference between them. But when you convert them to pH, that's the difference between pH 11 and pH of 12. And so that makes it a little clearer what's going on, right? And so we have this table of pHs, right? So standard substances tend to have pH that ranges from 0 up to 14, right? And so you've got pure water right in the middle of the scale at 7, and then you have things that get more and more basic, so seawater, baking soda, milk of magnesia, ammonia, soapy water, bleach, and liquid drain cleaner is the most basic. That's sodium hydroxide solution. That's going to have pH 14. It's basically totally dissociated. And then on the acid side, you have milk is a little bit acidic, 6.5, 6.8. A good lake has 6.5. Rain, if you have a lake that starts to get more acidic than that, then the fish start to die. So if the pH is below 6, then rainbow trout start to die. Rain is more acidic than pure water because rain has other substances in it that come down. You get the pH below 5.5, other kinds of fish start to die. Then an acidic lake or acid rain, these are very low pHs. They're starting to get very acidic, and at the 4.2, all fish are going to die. And then you start getting things that you know are acidic: orange juice, lemon juice, vinegar, and then you have extremely strong acids, sulfuric acid, hydrochloric acid is also similar to sulfuric acid here, and then battery acid is the most acidic, right? So the difference in concentration of hydronium ion between battery acid and liquid drain cleaner is 10 to the 14th, right? That's unimaginably huge. That 10 to the 14th is, 100 trillion, right? When numbers get that big, they start to get meaningless, right? Who knows what's the difference between 1 trillion and 100 trillion? It's hard to comprehend. They're just all big numbers at that point. So you use this logarithmic scale to define pH to make it on a scale that you can understand. Oh, I understand. pH 0, pH 14. 14 is very basic, 0 is very acidic, 7's in the middle. You can kind of work with that. Okay, so this is the reason we use pH. Okay, because it's a much more convenient way than talking about the actual concentrations of hydronium ion, which is actually what tells you how basic or acidic something is. Okay, any questions on this? Okay. Okay, so that's pH. Okay. So another application, so decibels. Um, so decibels and loudness. So in acoustics, the loudness of a sound is measured in decibels. And this is defined to be 10 times log of b to base 10, where b is the intensity of the sound measured in appropriate units of pressure. So that's force per square area. Um, so what does this say? This says that if the intensity of the sound is multiplied by 10, right? So let's say that we have some sound that has intensity, so you have one sound that has intensity B, which corresponds to 10, 10, ugh, no, ugh, no. 10 log 10 B decibels. Okay? Now, what happens if you have a sound that's 10 times more intense? So if you have intensity 10B, that's going to correspond to 10 log 10 of 10B decibels, which I'll abbreviate dB for decibels. And well, I can use my rules of logs, so that's 10 times log 10 of 10 plus log 10 of B decibels. Maybe I'll use this as an equals. Right? So I have a sound that's 10 times more intense, meaning it creates 10 times as much pressure. The waves create 10 times as much pressure. So I have this 10B. Well, log of 10B to base 10 is log of 10 to base 10 plus log of B to base 10. That's one of our rules of logs. And so that's exactly 10, 1 plus log 10 of B decibels, right? Because log 10 of 10 is 1. And that's equal to 10 plus 10 log 10 of B decibels. So what we have is that if your original sound is 10 log 10 of B decibels, whatever this is, our new sound is 10 log 10 of B decibels plus 10, right? So what that tells us is that if the intensity of the sound is multiplied by 10, that's what we just did here, we multiplied the intensity by 10, what that does is it increases the number of decibels by 10. It doesn't multiply it by 10, but it adds 10 to the number of decibels. Okay? So with pH, if you make something 10 times more basic, it raises the pH by 1. With decibels, it's scaled somewhat differently. If you multiply the intensity of the sound by 10, it raises the decibel measure by 10. Okay, so it adds 10. Okay, so here we are. Yeah, some applications of logarithms over here. Great. So I see some extra things. Yeah, logarithmic terms for algorithms, right? Computer science. I didn't even mention that, but worth talking about. So here's a decibels chart. Let me put it like this. So here's your decibel scale. So you have, at 0 decibels, you have no sound at all, right? And then over here, so breath, so just the sound of regular breathing is going to be 10 decibels. And what we see is each time we add 10 decibels, remember, you're multiplying the sound intensity by 10, right? So, A whisper is 10 times louder. Rustle of leaves is 10 times louder than that. Rain, refrigerator, conversation, a car, 70 decibels. A truck is about 10 times louder than a car. 80 decibels, that means if you have 10 cars, it makes the noise of about one truck. Uh, then hair dryer, helicopter, trombone right in your ear, a siren, a jet engine, and fireworks, right? So these are all, each one of these is about 10 times as intense as the previous one. Okay? Okay. So each one of these is about 10 times as intense as the previous one. Right. Yes. So I wonder what is the ambient decibel level at red light market? It's probably somewhere around 75 or 80. Right. So again, this is a scale. Something here, a jet engine at 130 decibels is a trillion times louder than a breath at 10 decibels. Right? I mean, this would be, roughly this is some sound intensity of, 10 to the 13th of some unit. And over here you have 10 to the 1 and 10 to the 2, 10 to the 3, where this, if this level is intensity, yeah, let me try to write that better. If this is your intensity, that's over here. So in some unit, which I'm not going to tell you exactly what the unit is, you scale it so that you get these correct levels. But right, you've got 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th, 10 to the 8th, 10 to the 9th, 10 to the 10th, 10 to the 11th, 10 to the 12th, 10 to the 13th, and 10 to the 14th. So you have huge, huge variations in sound. And if you just report it directly in terms of intensity, you'd say, oh, well, this has an intensity of like 30 billion, and this one has an intensity of 1 million. And what does that mean? It's just very, very hard to make any sense of those distinctions. But if instead of 1 million, that's 10 to the 6th, you say it's 60 decibels, and instead of 30 trillion, you say, well, a trillion is 10 to the 12th, 30 trillion, so 10 trillion is 10 to the 13th, 30 trillion is going to be about 10 to the 13 and a half. So if you said that's 135 decibels versus 60 decibels, that's again in units that people can understand. So these logarithms, these logarithmic scales, have the effect of compressing huge ranges in what your measurements can possibly be and putting it on a more civilized scale that people can make sense of. Okay? All right. Any questions? Any questions about this scale over here? Okay. Okay. So you're not hearing me. Okay. I wasn't talking for just now, but I was just waiting for any questions. Okay. So in order to make this scale, and this is the scale that's used throughout the world, you need logarithms to be able to do this scale. Okay. Third application. So Richter scale. Okay, so in cosmology, sorry, not cosmology, seismology, the magnitude of an earthquake on the Richter scale, we define that to be log of a to base 10, where a is the amplitude of certain waves that are detected by seismographs in appropriate units. I mean, an amplitude is just going to be a unit of length. So, when you have an earthquake, there's an instrument called a seismograph that detects certain waves. And however big those waves are, that's the amplitude of those waves. That's going to be this number A. And then when you take the log to base 10 of that number A, that's what's called the magnitude of the earthquake on the Richter scale. So what does this mean? So when measured by amplitude, an earthquake measuring a 6 on the Richter scale is 10 times stronger than one measuring a 5 on the Richter scale, right? Because 6 on the Richter scale, what does that mean? That means that log 10 of A is equal to 6, and that means that A is equal to 10 to the 6th. Whereas a 5 on the Richter scale means that log 10 of a equals 5, which means that a is equal to 10 to the 5. Right. Okay. So this is the difference, right? 10 to the 6th is 1 million, and 10 to the 5 is 100,000. So these amplitudes, which kind of correspond to the intensity of the earthquake, these amplitudes correspond to how strong the earthquake is. What seems like a small difference, oh, is the earthquake a 6 or is it a 5, actually corresponds to a tenfold increase in amplitude. And so, again, it's good to get a sense of what these things actually mean. So, if you look at the Wikipedia article on Richter scale, which I'll do now, so let me show you, there's a great table here on this Wikipedia article. So, if I do, Wikipedia Richter scale, there we are. Okay. So, here we are. So, there's this great table for the Richter scale over here. Okay, so you have what do you have on the Richter scale over here? So you have things that are a 1 to a 1.9. These are teeny tiny earthquakes that you can't even feel, but if you have a very sensitive instrument, it can detect them. 2 to 2.9, right, is a few people feel it a little bit, but basically doesn't cause any problems. 3 to 3.9 is like you feel the ground move a little bit, but it doesn't really cause any damage, but you might notice things shaking. 4 to 4.9 is you really notice things shaking. People are affected. It still doesn't usually knock down any buildings or anything, but some stuff may fall over. 5 to 5.9, now you're saying severe damage, it can cause damage if a building isn't made well, then the building can fall apart. But most a well-constructed brick building or something is not going to cause any problems, but everybody's going to feel it. 6 to 6.9 means that it can damage even well-built buildings. If you're building in an area with lots of earthquakes, so that's not most of West Africa, but if you're in the Western United States where there are lots of earthquakes, then you need to build things to earthquake code. Because if they're not earthquake resistant, then they can get severely damaged in a 6 to 6.9 magnitude earthquake. 7 to 7.9, you're getting into serious things. Most buildings are damaged. Some might collapse. Even if it's well designed, it's going to get damage. You can feel major damage can happen 250 kilometers from the epicenter. And remember, each time we go up a number, the earthquake's getting 10 times as intense. So it makes sense that we go up a number and things really change. So 8 to 8.9, major damage to buildings, lots of things going to be destroyed, will cause moderate to heavy damage, even to the best of buildings, extremely large area. There's usually only about one of these per year. And then as high as the scale really goes, 9 to 9.9, near total destruction. You have that in your city, the entire city is going to be destroyed, right? So, and it can go to very distant locations. And the key thing to remember is that each one of these numbers is about 10 times as intense as the previous number. And so again, we could talk about these earthquakes as having magnitude a billion or a million or 100 million or whatever, and it would be hard to understand. But we can understand that, okay, the Richter scale, an 8 on the Richter scale is really serious. A 5 or a 6 on the Richter scale is kind of serious, but as you get below 5, it's usually not that serious, right? It puts things on a human scale that we can understand. Okay, so all of these logarithmic things, pH, Richter scale, and decibels, what they do is they put measurements in science and they put them on a more human scale where we can understand this. Okay. All right. So, I mean, we're not really, I'm not really doing much math, but I'm just saying this is how these scales are constructed. Okay. All right. So let me go back. So this is the chart. Let me go back to the slide. Okay. So again, this is what we have. Okay. So any questions about the Richter scale?
Yes, sir.
Yeah,
Yes, sir.
Prince.
Yeah, this is what I have a concern with this letter A. So is this letter A representing the 10 which will raise the 6 over what the A stand for in this field?
It stands for amplitude. So this A here is the amplitude of the waves detected by the seismographs. So you have an instrument called a seismograph. It detects like how the Earth moves, and it detects waves. And A is basically saying how big are those waves that are detected by the seismograph. So it's a unit of length. Okay. And it's saying basically how big are the waves that the earthquake is creating. And so, 5 on the Richter scale, the waves are going to be 100,000 of some unit. I'm not telling you exactly what the unit is. It doesn't mean 10,000 meters. It means 10,000 times some base unit, which they use to define the Richter scale. I'm not so worried about the absolute version of what it means. I'm talking about the relative version. Whatever that unit is, a 5 on the Richter scale means 10,000, 100,000 of that unit. A 6 on the Richter scale means a million of that unit. Okay, which means that a 6 on a Richter scale means that this amplitude is 10 times larger than what you would have with a 5 on the Richter scale, right? Whatever the unit is, this is 10 times as long as this. Okay,
Okay.
and this pattern repeats itself. So every time you go up one number on the Richter scale, this amplitude is multiplied by 10. Okay.
So that means the amplitude has a number which is top two. Like say for instance, you have a number that it has the starting point and then the ending point. For instance, if maybe to raise from 1 to 10,
Yeah.
or is it has an estimated number that you can only stop to. That's it.
Yeah, I mean, yeah, so the amplitude, I mean, so you're just gonna, this amplitude is measured in some sort of units. So let's say that I measured an earthquake and the amplitude was, I don't know, 96,423, units, whatever they are. These units are like millimeters or something like that. I mean, they're not, they're just some unit of length, okay? Which if you want to go into the details on the Richter scale, you can see what these units are. But it's just some unit of length. So then to find the Richter scale, I have to take log base 10 of 96,423. This is probably going to be just a teeny tiny bit below 5. So let me see, log base 10 of 96423. This is, 4.98. Okay. So if this is the amplitude, that converts to 4.98 magnitude on the Richter scale. Okay, so it's just a way of going back and forth between amplitude and Richter scale, where amplitude is the fundamental physical measurement. It's how much the Earth is vibrating. It's the amplitude of those waves, how far they go. But we use a logarithm to transform it into units that make more sense to people. Okay, so instead of saying that this is an earthquake of 96,423 units, which people might not understand, we say this is a 4.98 on the Richter scale. And that's a little bit easier for people to grasp what it means. You can just look at your chart and say, oh, 4.98. That means, maybe some houses might get destroyed if they're not well built.
Okay, thank you. So next question is, sir, sorry,
Yeah.
but I just want to understand this good. So
Mhm.
the law, we have a law, the base of 10 of the logarithm. So
Yeah.
can the logarithm of the base, which is 10, can it be different number like 2 or
I mean, you can make it a different number, but it just wouldn't be the Richter scale. I mean, the Richter scale is what people use throughout the world, and it uses 10. You could make a scale where the base of the log was something different, but it just wouldn't be the Richter scale. It would be something else, right? So the Richter scale, by definition, uses 10 as the base.
Okay, thank you so much.
Yeah,
Thank you.
no problem. And a lot of these things are using 10. So the decibels is using 10, the pH is using 10. This is what's called the common logarithm, and it's usually just the most intuitive thing to use. So that's why people use it. And it's just a convention. I mean, there's nothing mathematically correct about using 10. It's just a convention. It's how people state the Richter scale. If somebody had wanted to use 2 instead, and a lot of times in computer science, you do use 2 to measure algorithm times, you could use that. You could use 2, and that would be totally fine. Okay, but we use 10
Thank you so much.
because that's the world's convention. Okay. All right. So music pitches. Worth knowing also, so the pitch of a musical note it also has to do with waves. It's the frequency of its wave vibrations. This is measured in hertz. It's vibrations per second. So hertz means, vibrations per second. Okay, this is what tells you the pitch. And so if you have a piano with 88 keys, it has a lowest note. That note's sometimes called A0, which has a frequency of 27.5 hertz. The highest note, which is sometimes called C8, has a frequency of 4186 hertz. And the ratio of frequencies between, if I take two notes on the piano that are right next to each other, then the ratio of their frequencies is 2 raised to the 1 over 12. I should tell you what that number is. So 2 raised to the 1 over 12 is this is roughly 1.06. Right? It's roughly 1.06. Okay, so this is the ratio of frequencies between any two notes on the piano. And so if you have two notes that are 12 keys apart, then each successive ratio is 2 to the 1/12th. So you take the ratio between one piano key here and another piano key that's 12 keys apart is going to be 2 to the 1/12th raised to the 12, and the 1/12th and the 12th combine to give you 1, so this just becomes 2. So if you look at a note on the piano and a note 12 notes above that on the piano, then the frequency of the higher note is double the frequency of the lower note. Okay? So for instance, there is a key on the piano with a frequency of 440 hertz. And if the keys are numbered from 1 to 88, from lowest to highest, which key is going to be this key with this frequency? So I'm just going to solve this because we don't have that much time left. So the idea is we're going to number the keys. We know that key 1 equals 27.5 hertz. So that means that key n should be equal to, well, each time we go up one note, we're raising the frequency by a factor of 2 to the 1/12th. So key n should be 27.5 hertz times, well, key n is times 2 to the 1/12th raised to what power? Well, how many notes do you have to go up to get from the first key to the nth key? Well, you're going up n minus 1 keys. So it's 2 to the 1/12th raised to the n minus 1. Okay? So I'm going to recopy this formula on the next page, and we're going to solve, which note is this 440 hertz. Okay, so this key n is going to be the lowest note, which is 27.5 hertz, and then for each number that you step up, you have to multiply that by 2 to the 1/12th. So you have to step up n minus 1 notes in order to get to the nth note, right? You start with 1 and you go up n minus 1, that gets you to n. So let me solve this question. So we recall, key n has frequency 27.5, I won't write the units now, times 2 to the 1/12th to the n. So what we want to solve for the problem is 440, right? The problem said there's a note that has a frequency of 440 hertz. What note is that? So 440 equals 27.5 times 2 to the 1/12th to the n. Sorry, to the n minus 1. If we divide both sides by 27.5, it turns out that this gives us 16 equals 2 to the 1/12th to the n minus 1, or another way of saying that is that's 2 to the n minus 1 over 12. Okay, so 2 to the n minus 1 over 12. Okay, Festus, you'll get data distributed to you for next time. So now how do we solve this? Going back for a long time, you have to take the logarithm of both sides. So I'm going to take log both sides to base 2. So I get log base 2 of 16 equals log base 2 of 2 to the n minus 1 over 12. So what does that tell us? Well, log base 2 of 16 is 4, right? Because 2 to the 4th equals 16. Log base 2 of 2 to the n minus 1 over 12, well, we use this exponential rule. That's n minus 1 over 12 times log base 2 of 2, right? I move the exponent over here. And so this log base 2 of 2 is just 1, so that tells me that 4 is equal to n minus 1 over 12. And that tells me that 48 is equal to n minus 1. I multiply both sides by 12, and that tells me lastly that 49 equals n. Okay, so this note that has 440 hertz is the 49th note on the piano. Okay, and that's called concert A. Sometimes that's an orchestra that's the note that the instruments play to tune themselves. Okay, so at this point, you're just solving an algebraic equation, but to do it, you need to use logs. Okay, you need to use logarithms in order to figure out what note this is going to be. And so all that I want to, it's not that like finding this out is so important, but I just want to impress on you that the way that musical notes are determined, when you're going da 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 da, all of these frequencies are being multiplied by a constant. Each time you go up one note, you're multiplying by this frequency, which you're multiplying by this scaling factor, which is about 1.06. It's 2 to the 112th. Yes, James?
Yes, there's something I want to. How you manage to get a 12? A 12.
Yes, so
I
what's
said, how you manage to get a 12?
Oh, the 12? That's
Yeah.
just the way it's defined.
Oh, so
This is just how Western music works, right? So Western music, has what's called a 12-tone scale. And it's just
so
that's the
that
way
means
they've decided to divide up the notes, right? It's just decided to take an octave, which are two 12 keys apart, an octave, which one note is double the frequency of the other. And in Western music, that tends to just be divided into 12 equal parts. That's just what people decided. There are 17 note scales, there are 31 note scales. There's various Asian systems have different ways of dividing things up, but for Western music, 12 is what's always been used.
so that the number of octaves you multiply by the number of key.
Exactly. So 12 keys makes an octave. So an octave is a factor of 2. So just the difference between two little keys is going to be not a full factor of 2, but 12 of those will make a factor of 2. So each one is a factor of 2 to the 1/12th. Because when you multiply 12 of them together, you get a factor of 2.
Okay.
Yeah. So
Thank
if you
you.
look on a piano, there's 12 notes in between each octave. If you count both the white keys and the black keys. Yeah, we're always counting all the white keys and the black keys in this exercise. Okay. So just another thing where these logarithms, where they show up. And I'll show you again, we have a little graph here, which I'll show a little chart. Wait, what did I want to do here? No, 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 no. No, what did I do? What did I do? Sorry. What did I do here? Sorry. Let me share my screen. No, what did I do? Share screen. Okay. Here we are. Okay, so this is just another chart, which maybe is not so important, but this is the keys on the piano are in the left column, so they're just numbered one up through 88, and then it shows in this column. So this has like the name of the key, the name of the note in music notation, but in this column it tells you what the frequency is for each note. So we start with 27.5 on the very bottom, that's the lowest, and then they get higher and higher and higher and higher. This is this 440. That's the 49th note, as I had mentioned before. So this 440 here is is the 49th note. That's called A4 or A440. And then as you go up, you get to the highest note on the piano, which has this frequency of 4100 hertz. And the highest note is getting toward the highest frequency that humans can really hear, and the lowest note is getting down toward the lowest frequencies that humans can hear. Dogs and other animals can hear much more. And this is just for other instruments. So guitar and bass and cello and viola and violin. It also has, what strings correspond to what notes over here. So if you have a guitar and you have your high E string on the guitar, then that's the highest sounding string. That's vibrating at 329 hertz, and that corresponds to the 44th key on the piano over here. So if you're interested in music, this is, a nice chart about these things. Okay. So, all right. So I want to finish up soon. Okay. So let me give, yeah, this is going to be the last thing that we do today for math. Let me just do this example and maybe we'll go over it a little more next time. So an example of a word problem would be, suppose a car driving by makes a sound measured at 70 decibels. Then how many cars would need to drive by at the same time to yield a sound level of 78 decibels? And we're going to assume that if n cars drive by, the intensity of the sound is multiplied by n. So let me just recall that the decibel measure is equal to 10 log 10 of b, where b is equal to the intensity. Okay, this is this measurement that we had. Okay, so this is going to be the last thing that we have. Okay, so 70 decibels means we're solving 10 log of b to base 10 equals 70. And that means log of b to base 10 is equal to 7. And that's just saying that b is equal to 10 to the 7th. Okay, what about 78 decibels? That's saying I'm going to use a different letter for this. Let's say that 10, and so we want to solve that 10 log base 10 of NB is equal to 78, right? Because we're trying to solve for N. If N is the number of cars that drive by, so if the intensity of a 70 decibel sound is one car, that's 10 to the 7th. This is one car intensity. Then this over here is N cars intensity. Okay, and so we want to solve this for N. So let's see what we have. Well, this is 10 log 10. Well, log 10 of NB is log 10 of N plus log 10 of B. We want to solve that this is equal to 78. Well, that is going to be log 10 of N plus log 10 of B is equal to 7.8, right? I just divide both sides by 10. Well, log 10 of B, we know what it is. We decided that it's 7. So B here is, I'm going to say, intensity of one car. So this log 10 of B over here, we already know what it is. This equals 7. Okay, so this is going to tell us that log n to base 10 is equal to 7.8 minus 7. That's equal to 0.8. And that's going to tell us that n is equal to 10 raised to the 0.8. That's what a log is. And what does that mean? What's 10 raised to the 0.8? That is about roughly 6.3. Okay, so what this is telling you is that it would take about 6 or 7 cars together to raise the decibel intensity from 70 up to 78. And so this is important when people are trying to design a system, a highway system, and want to know how much noise it's going to make. You need to know kind of how loud is a standard vehicle, and then how loud are multiple, how loud is it going to be when 100 of those vehicles are driving past, or when 200 of them are driving past, or whatever. So this gives you a sense of what happens. So to raise the sound level by 8 decibels, that's equivalent to having 6 cars drive by at the same time, or 6.5 cars driving by at the same time. Okay, so one car gives you 70 decibels, which means intensity of 10 to the seventh. If you have 6.3 cars, that's going to give you intensity of 10 to the 7.8, or 78 decibels. Okay. So the decibel this is what you do. You just set up the equation. You're trying to solve for n. So the total intensity is NB. You set up the equation using a log based on, how the number of decibels that you want.
So you run it n to the nearest whole number.
Yeah, you can round it to the nearest whole number.
Run it
So
n.
roughly, it says roughly.
Okay.
So you could say 6 or you could say 7. I'd say both of those are fine. They're roughly, if 6 or 7 cars drive by, that'll give you the right thing. So yeah, so we could round this. We could say round to 6 or 7. Okay. Okay, good. Okay, so let's finish up because I think people's batteries are running low. So the question is, again, similar to last week, come up with a word problem involving an application of logarithms and solve your problem. Okay, so something similar to this. So, excuse me. So something involving decibels, or involving pH, or involving music, or involving the Richter scale, or if you have a favorite application of logarithms, you can come up with a word problem involving there. But this is so this is the homework, and we have a while to do this because our next meeting is not for 3 weeks. So this is on the syllabus, but the next meeting is on October 9th, and we're going to begin a short unit on geometry then, but we'll also spend a little bit of time reviewing this logarithm stuff because I don't want it to just get lost. Okay? So that's going to be our next meeting, and I wanted to say one more time. So first of all, congratulations to everybody who will be certificated next week, because we're not going to meet between now and next week. So I want to offer my congratulations, everybody from last year and the year before. And then I want to remind everybody, I guess Deborah's still here. Do you want to just repeat what you said at the beginning, because some people didn't join until later on, about the certification?
Yes, the program will be 2-4. We'll have Monserrato the 25th, and we have Nima the 26th. So we will communicate the venue to everyone when we are done with the process, the planning. So those that didn't receive the certificates for the past time, every will be given next week. So everybody will be there for the program, and we have some educational stakeholder that will attend the program to certificate you guys. So thank you again, Tata Opos.
Okay. You're welcome. And yeah, so when you get the venue, if you can come, please RSVP to Deborah so that she knows how many people will be there.
Hello, sir.
Hello, Rush.
Yeah, pertaining the certificate issue, I don't know. Can the mother please help us with name, because maybe some of the name, but without the actual name that we know on social media.
Sorry, I don't think I understood, but maybe AB or Deborah can answer.
Come again with a question.
Hello, yeah, you come back with a question. Hey, come back with a question. Come back with a question.
I said that the pertaining the certificate issue, maybe some of our name that go using Raj, but my real name is Rashid.
So
No,
the name,
Raj if your name was rushed before, we cannot change any salary because salary are already been signed. So as you come, what you're going to be receiving under that name, you're going to be receiving for under that name.
Yeah, because we listen, every time we can put a tenner on the rest of this.
Yeah, that what we always telling you people, all the teachers, that send your name and your WhatsApp number. That be a full name. It shouldn't be somebody else's number, or it shouldn't be somebody else's name. Okay, so as you say your name, and we have to give the certificate under that name because certificate are already been printed.
Okay.
So,
Emmanuel, the question?
Andrew?
Yeah, AB.
Andrew?
Yeah,
Thank you again.
This
Thank you
semester
again.
was eight.
All right. You're welcome. Emmanuel, do you have a question?
Yes, I said this going semester I was in, but close to the closing of the class, my phone got missing, and I was thinking as to whether this cycle or this certificate that is about to be distributed as to whether I'm kind of puzzled.
Okay, Andrew, we're going to look through the certificate. If your certificate is there, but you should be part of the program. Come there to see whether your name is there. But we're going to check it and list and give a listing of people that are going to be having a certificate. We're going to also list it all in the chat room.
Right. Yeah. So you list the name of everybody who has a certificate, right? Because you have them, right?
Yeah. We're going to do
So
that.
you can list everybody's names, and then if your name is on that list, then you can respond and say, are you coming or are you not coming?
Yeah. But we want for everybody to be there. Let it be a program that everybody will be attending that, because some stakeholders will be there. So you come and at least make the people to understand that you are doing a math program.
Okay. Good. Okay. So I think that's clear. And I'm sure we'll have more chatting on the WhatsApp to clarify everything. But yeah, again, this is the last session before the certification. So just wanted to make sure that we could take care of everything now, all of the questions.
Okay. Thank you, Andrew.
Okay. Thank you, AB.
We're going to talk again.
All right. Sounds good. Okay. So any questions about any of the math from today before we finish?
Yeah, hello there.
Yes, Hassan.
Yeah, I have a question.
Mm-hmm.
Is radioactive decay also a logarithm?
Yeah, I mean, usually you phrase it as an exponential. So exponentials and logarithms are really the same thing. It's just a question of which quantity are you solving for which other quantity. So yeah, so if you have a radioactive decay question and you want to know how much time it's going to take for a substance to decay a certain amount, that's going to be solved using logarithms. Right. So I would normally say the equation that governs radioactive decay is really an exponential equation. When you write it down, it's, e to c e to the kt, where c and k are some constants. So it's an exponential equation. But anytime you want to solve an exponential equation, you have to use logarithms to solve it. So in that extent, it's also an application of logarithms. The things that I did today are where the equations themselves are given in terms of logarithms. Right. So that's why I did those examples today. The radioactive decay from last year, the examples are given in terms of exponentials. The equations are in terms of exponentials, but you still need logarithms to solve them.
All right, thank you.
You're welcome. Okay. Yes, Armstrong. Yes, the certificates are for the past 2 years. So you'll get your certificate for 2024 and for 2025. Yeah, so it's both years' ceremonies together. So if you participated both years, you'll get 2 certificates, one for each year. Okay.
Hello.
Hello. Yeah, Marcus.
Yeah. So, Dr. Obas, thank you so much always, and much appreciate for the knowledge. And okay, I think you sent me my 2024 certificate in my inbox, and was it signed? I don't know what it will be the
Because
same with
I don't.
me, with
Okay.
me.
Yeah, you need this. I could only sign my file. If you want the signed certificate, you're going to have to get someone. You're going to have to get Aby or Deborah to take a picture and send it to you. Because I make the certificates and I send them to Liberia, and then they get signed in
Yeah.
Liberia. I don't have access to the signed certificates. So,
Oh, okay.
so if you want
Yeah.
a
So
copy of the
I
signed
already.
one of them will need to take a picture.
Yeah. So I have Sati, Mr. Sati, and he has my other certificate. So maybe I've informed him that anytime during the certification, so he can get mine, because if someone coming here, I'll try to, communicate with him so he can give to the deposit of Brigadier Law.
Okay, perfect. Yeah.
Yeah.
Because I only have the I mean, I sign it before I send them off,
Yeah.
but
So that
the
means
master signature, I
that I
don't have.
need 2024. So that means I need 2024 and 2025.
Yeah, that's right.